Okay, we'll do it here. So the element integral integral over omega e whi rho second time derivative right, this one. I'm going to go straight away into writing it out with our basis functions and summing over basis functions and all that sort of thing. Okay, so we know that this is integral over omega e. Actually, let me skip some more steps, okay, because we're now such experts at this that we don't really need to write every single thing. Okay, let's do it this way. Fine. Sum over a comma b c a e I. Okay, and you recall that c a e I is, each of those is the ith degree of freedom at the 8th node of element E. Okay, this integral over omega E NA, let's have the rho there, NA NB dV, and outside of this integral come the degrees of freedom that are used to construct the representation for the trial solution, right? So that will turn out to be dB element E degree of freedom I. Okay, and what is implied here is a sum over our spatial dimensions I. Okay, now the form that I have in parentheses on the right hand side, okay, the everything including the integral, is what we'd identified previously to be the AB component of the consistent mass matrix. Okay, the same thing happens here, except for the fact that there is one thing we need to account for, which is that there is a sum over I here. Okay, so let me just mention this here. Recall sum on I. Okay, and what that does is lets us write this thing out as sum over a comma b c a e I integral over omega e rho n a n b dv. But now what I'm going to do is, I wrote that dv too close, I'm going to slip in here a Kronecker delta. Okay, just allow me to do this and I'll show you why I'm doing this. Okay, since I've slipped in that Kronecker delta and given it indices ij, I'm going to turn the dBEI from the previous line, this one, into dBEJ. Okay? All right? As a result, now when we put this all together, what you see is that, what you observe is that though the contributions to from the integrand are the same as we had for the linear parabolic problem with a scalar unknown, right? What we've done here to account for the fact that we have vector unknowns is to include this Kronecker delta right there. Okay? All right? Now when we put everything together, we get the following. Okay? We're now, in what I'm about to write, I'm going to abandon the explicit writing of the sum over over A and B. Okay? And in fact, let me give myself more room here. Just before I go ahead and write that, I note that I've forgotten the second time derivatives on the D to account for the fact that we have a second time derivative right there. Okay, now everything's fine. Okay, so the way I'm going to write this by dropping the explicit sum over a and b is the following. I get C1 E, right, transpose, okay, C2 E transpose, so on up to C number of nodes in the element E transpose. Okay, this one, for instance, C2E transpose is simply C2E1, C2E2, C2E3. Okay, right? All of that now multiplying some big matrix, which makes up our mass matrix. Okay, and out here we get our vectors or vector of D1E double dot, D2E double dot, all the way down to DNNE element E double dot. Okay, and like I did here for C2E, let me just point out that this is the little vector D2E1 double dot, D2E2 double dot, D2E3 double dot. Okay? All right. Now, note that for each combination of nodes from the C vector and the D vector, okay, we get a little matrix, okay? And that little matrix is obtained by writing out here we have here, let me show you what we get here. Okay, we have here a little matrix which is rho NA NB dV over the element, and let me make this actually N1 N1 to show you the very first combination. Okay, but this matrix, that integral itself multiplies what you may call the 3 by 3 identity matrix. Okay, that's because it's this matrix that I've just written, that little sub-matrix that I've just written, which multiplies, which sort of intercedes in the multiplication between C1E transpose and D1E double dot. Okay, now this continues until we get another such matrix, right? Each of these blocks is a little matrix, right? Each of these is an integral over omega E of n something else, integral over dV. Okay, all right, all the way down. So we have how many such blocks, right? We have nne such blocks in the column-wise direction and nne such blocks in the row-wise direction. Okay, all right. All right, and what's important to note is that each of these little matrices is itself an identity matrix, right? And this is what our Kronecker delta does for us. Okay, and so the general term in here would be something like integral over omega E rho NA NB dV 1 0 0 0 1 0 0 0 1. Right, you'd get other such block matrices everywhere. Okay? All right? And this matrix that I've written out here is our element mass matrix, okay, in consistent form, okay, the consistent mass matrix. All right, so this is an important thing to note. This is slightly different from what we saw for the linear parabolic PDE, where each degree of freedom is essentially a single scalar unknown, right? And in that case, this identity matrix essentially collapsed to the scalar 1. Okay? The fact that we're dealing with vector unknowns here just has essentially expanded that scalar 1 into an identity matrix, right? A 3 by 3 identity. That's all. Other than that, everything is the same. Okay? It's probably useful for us to ask what are the dimensions of ME? Okay? What would they be? Right, the dimensions of ME are number of nodes in the element times number of spatial dimensions squared. Right? Those are the dimensions of ME, right? Dimensions. Right? Okay? That's it. This is our element mass matrix. Right? The only thing that's different with regard to what we've seen before. Assembly works just as before. Assemble over degrees of freedom. Common degrees of freedom across elements belonging to the same global degree of freedom implies that those corresponding matrix contributions from from the neighboring elements add up. Okay? All right? So let me just state that here. Assembly proceeds as before over global degrees of freedom. Okay? What we're left with finally at the end of the process, right, after we say that, well, this has to, our weak form has to hold for all C belonging to the appropriate Euclidean space, right? What we get at the end of it is the following set of equations, right? We get M d double dot plus KD equals F. Okay? When we were not doing elastodynamics, but essentially elastostatics, this first term was missing. Okay? It's just shown up now. Right? Everything else is the same. We know that boundary conditions are buried inside here, right? Including time-dependent Dirichlet boundary conditions. That also works just as we saw earlier, right? In the case of the time-dependent parabolic problem. Okay? If we have Dirichlet conditions, they are time-dependent, well, we know exactly what they are at every time, at any time, right? They would go to the right-hand side. What we would have here, in addition, are initial conditions, right? D at 0 equals the vector of, well, it essentially equals the vector formed by taking every Dirichlet condition at degrees of freedom lying on the corresponding Dirichlet boundary and putting them all in a vector D naught. Okay? We did this for the parabolic problem. We need another boundary condition here, sorry, another initial condition because we are second order in time. That's D dot at time t equals 0, right, which we will denote as V naught. Okay? All right? And V naught, you remember, is simply it's simply constructed of u dot, sorry, it's actually, I think, just the value of the function V naught, right, at points x A, right, for every degree of freedom A that lies, for every single degree of freedom A, right? Because the initial condition has to be specified over the entire vector D. Okay? This is essentially it. Right? Just as we specified initial conditions for our parabolic problem, we have two initial conditions now for this problem. All right? Okay. So that's really all we need to know about how the matrix equations are obtained. The process is exactly the same. You get another mass matrix. There's some detail in the mass matrix. It's for corresponding to every combination of degrees of freedom. It's slightly blown up. We have that little 3x3 identity matrix sitting there, and we have two initial conditions, right? And we know how to specify those initial conditions. So really that's what we need to know. We'll stop this segment here. When we return, we will talk about time discretization.